there is a boundary. There is like a big soap bubble between, me and my cookie or whatever. There'll be no way of getting from here to there without crossing that surface. So that's called codimension 1 object. So those are easy to find. Now, in 3-dimension, when you shoot pool, it's relatively easy to hit another ball. But in 3-dimension, when you have to throw the ball, it's much harder to hit it. And in 4-dimension, it's very hard to hit the ball, even though you don't have experience. So these objects could be hard to find, but once you find them, they're very powerful, very helpful to have. So once you find them, you go and look what happens in their neighborhoods. So first you find they do nothing, they're equilibria, but what happens if I hang around? That is an easy problem once you have them. That's called stability matrix. And we are very good in this book. It's totally trivial to compute it. It's 3-dimensional, but for example, when we studied turbulence in million dimensions, we are able to find the most important eigenvalues, even of these huge matrices. So that stuff is accessible. And it tells me what happens in a neighborhood. Generally has some form of a matrix with real coefficients, unless you're doing quantum mechanics. And it's a d by d matrix. And, much of applied math and Google algorithms and all other nonsense that we have to do today is based on finding eigenvalues of such objects. So there are many, many methods. And you find d-dimensional matrix, so you have to find, d eigenvalues. The sum of them might be degenerate due to symmetries. And now the unpleasant thing that happens when you do that is that these eigenvalues, you started with a real system, everything is real. You expect them to be real. But Tartaglia says in 16th century, they can be complex, they can have imaginary part. And for humans, this is very hard to understand for some reason. But it's a fact, fundamental theorem of algebra that would say the real or the coming complex pairs if everybody was real to start with. And now there is a very powerful way of using that data that you should always use. What you do is, this is kind of nice because these are either 1 or 2-dimensional numbers. So you can write them in a complex plane. But this is real part and imaginary part. And if you find 1 or 2 or 7 positive real lambda, real eigenvalue pairs, you really care about these guys. They're really the most important things when you try to control the world around it, because they're unstable. And in engineering, they're often bad news. So one criterion when they're bad news is that you try to build a magnetic levitation train. It's a mechanical system, so you can perturb it and you can compute the eigenvalues of how the linearized magnetron, magnetic levitation train behaves. And if it has unstable directions, you're screwed because your train will just exponentially fast jump off the tracks and be a wreck. Now, if you happen to have like $300 billion and you want to solve the energy problem by creating a fusion device, today that's done by sending plasma in magnetic fields in tokamaks and similar devices. And if you have an unstable mode of that plasma, that's terror because it'll melt the very expensive tokamak and produce very nasty radiation for next 100 to million years. So you don't want to have that. So that's where engineers are unhappy about being unstable. Now, suppose you're trying to send somebody like Perseverance to Mars. You could be a fool and you could just build a big rocket and you say, I'm here, Mars is there. I go directly to Mars. Only fool would do this. What you do is you use the intrinsic instabilities of solar system. So between planets, there are so-called Lagrange points, and there are more sophisticated versions which are not points, but cycles or surfaces or hypersurfaces of instability. Because when you get to the Lagrange point, if you nudge your system a little bit to the left, 1 inch, it'll go to Jupiter. But if you nudge it 1 inch to the right, it'll go to Saturn. And you can basically travel the whole solar system for free just by being intelligent, by going from one unstable Lagrange point to another one and just being kicked and using very little fuel to get from here to there, just being slung around. So that's what's good about chaos. If you have a positive attitude, it actually makes it possible to do things you wouldn't do otherwise. And that's what you do when you're dancing. You do it all the time without thinking about it. You use instabilities. Walking, very important that you're unstable while walking. But go to technology. Whenever I find equilibrium, I should compute stability matrix. Then I should plot its eigenvalues. Now, if they're unstable, they'll be real. If they're stable, they'll be real and negative. And the further you go to the left, the more stable you get. So here is a world of very stable directions in your neighborhood. And you could be, a million-dimensional neighborhood because you're describing fluid in terms of lots of little volumes of fluid. So that's a high dimensional. And this will have a property that you won't care about anything that has this eigenvalue because they'll just die like a ton of rocks. There'll be nothing to it. But then they can be complex. So, for example, you can have a pair, and because this matrix has real numbers, its characteristic polynomial has real coefficients, and that means complex pairs. So they have the same real part, and they have a complex conjugate, so equal in magnitude complex part. And we have already seen them. What they do is the spiral. So the first interesting thing, and very, very important thing, and again, something that you know intuitively from your experience, but you might not have seen, it's called a Hopf bifurcation. So that's a genuinely two-dimensional thing. Why is it that we can live in a very high-dimensional world and still have rather simple control mechanism? It just has to do with this division between stable and unstable. If there are a few unstable directions, then I can work very hard to control them. So if my levitation train goes a little bit to push, I can push it back if I understand the dynamics in detail. So it's the essence of control theory, is just to care about unstable things. Stable ones take care of themselves. If I am having a flock of sheep, from the unstable direction, they all come together and then they, stretch themselves around a road or something. But so the stable directions are helpful, but you don't have to worry about them. They're just like good children that take care of themselves. That's why lots of problems can be done by Strogat's method of 1, 2, 3 dimensions, which is all we'll do in this course, because that's the beginning of the trouble. That just has to do with how many of these dimensions can be unstable, and typically on the boundary between things being stable and starting to fall apart, they fall apart by, as you change your parameters, everybody moves toward the unstable, and somebody crosses from being stable to unstable. That's called a bifurcation. And you cross through this point, and then you have to worry about them.